Assalamu alaikum wa rahmatullahi wa barakatuh. Hello, grade 10. Welcome to our chemistry revision. Let's start our revision with the thermochemistry. In thermochemistry, as we know that thermochemistry is a branch of thermodynamics which study the change in heat associated with physical process and chemical reaction. The law of conservation of energy will be applied more in thermochemistry because, as we know that energy is neither created nor destroyed, and thermochemistry is studying the change in heat. So if you are doing any experiment related to thermochemistry, you have a system in which you are doing the experiment or on which you are studying, and the surrounding, so the rest of the universe which is surrounding the system. We have three types of systems: the isolated system, and the open system, and the closed system. The isolated system doesn't allow any change in energy or matter. The open system allows both a change in energy and matter. The closed system allows only the change in energy, but doesn't allow the change in matter. Example for the isolated system, the calorimeter that we are going to talk about later. The open system, that like a hot cup of tea that you have, when evaporates, it exchange energy with the surrounding and exchange also matter with the surrounding. The closed system, such as the thermometer. The thermometer doesn't allow the exchange of matter, but allow the exchange of energy with the surrounding. The first law of thermodynamics says that the total energy in the isolated system stay constant, even if it forms another state, even if the state of the system is changed. Here we have a very important law, which says that the change in energy of the system should be equal to the change of energy in the surrounding, but with what? With opposite sign. Why? Because when system lose amount of energy, the surrounding gain this amount of energy. So the system lose, but the surrounding gain the same amount of energy, but with opposite sign. If the system gain, so the surrounding lose, and so on. The difference between heat and temperature. Heat, the amount of energy transferred from object with high heat content to object with lower heat content. But the temperature is a representation for what? For the kinetic energy. So if object has high temperature, means it has high kinetic energy. If object has low temperature, means it has low kinetic energy. Here we have an example. We said that we have a system contain A and B substances. So here we have a system which contain inside it A and B. He said that substance A, the change in substance A, that it releases amount of energy of what? -60. And B, absorb amount of energy of 40. Usually the sign of negative mean release, the sign of a positive mean absorb. -60 A and B, so we are going to calculate what? The change in energy in the system. So it equals what? -60 plus +40. So it equals -20 kilojoule for sure. We have the rule which says that the change in energy of the system equals negative the change in energy of the surrounding. The change in energy of the system equals -20. So the change in energy of the surrounding will be -20. That means the energy of the surrounding will be +20 kilojoule. So the system in that example release amount of energy, which is 20 kilojoule, which is absorbed by the surrounding. The measuring units of heat. For the measuring units of heat, we use two units to express the heat, joule and calorie. The calorie is the amount of heat which is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. 1 gram of water by 1 degree Celsius. Joule, the amount of heat which is required to raise the temperature of 1 gram of water, but with what? With 1 over 4.184 degree Celsius. 1 joule equals what? 1 over 4.184 of calories. So 1 calorie, we can say that 1 calorie equals 4.184 joules. 1 calorie equals 4.184 joules. So if we are comparing between the amount of heat represented by calorie and the amount of heat represented by joule, so the amount of heat represented by calorie is greater than the amount of heat represented by joule. Specific heat is like a fingerprint for each substance. Specific heat means the amount of heat needed by 1 gram of a substance to raise its temperature by 1 degree Celsius. The specific heat is different from one substance to another. What is the unit of specific heat? Its unit is joule per gram degree Celsius and joule per gram degree Kelvin. But the one which is mostly used is joule per gram degree Celsius. So specific heat represents, again, the amount of heat required by 1 gram of matter to increase its temperature by 1 degree Celsius. Here we have a very important information that water has the greatest specific heat on Earth's surface. So raising the temperature of 1 gram of water need much amount of heat. Here we have an example. All the following table illustrate the specific heat of some elements in joule per gram degree Celsius. Aluminum 0.9, copper 0.38, iron 0.44, carbon 0.71. He said when equal masses of these elements are exposed to the same quantity of heat, the element whose temperature rises faster is what? If we analyze each number, so for aluminum needs 0.9 joules of heat to raise the temperature of 1 gram of it by 1 degree Celsius. Copper needs 0.38, iron needs 0.44, carbon needs 0.71. So the one who needs least amount of energy is what? Copper. So if we apply the same amount of heat in all of them, the temperature which rises faster will be the temperature of copper. The one which rises faster is the temperature of copper. The calculation of heat amount law. This is very important law that you are going to use in this part of thermochemistry many times. So here the Q, which represent what? Quantity of heat. Q represent the quantity of heat. Q equal M, which represent mass of substance. C represent the specific heat of the substance, and delta T represent the change in temperature. Okay, so by using this, here we have an example. If the temperature of 1 mole of pure water rises by 2 degrees Celsius, the quantity of heat in calorie. Take care that he is asking us to calculate the heat in calorie. Is 9. So the specific heat capacity of water, equal 4.18 joules per gram degree Celsius, okay? And the specific heat of water also equals 1 calorie per gram degree Celsius. So we are going to use this rule, which says Q equals MC delta T. But here we don't have mass. We have the number of moles of pure water. So we are going to calculate mass of water, which equals mass of water equals number of moles, which is 0.5, times molar mass, which is 16 plus 2 of hydrogen, which is 18. So the mass of water that we have equal 9 grams. Move again to the rule, which says that Q equals MC delta T. As he is asking us to calculate the heat in calorie, so it's 9 times the specific heat in calorie equals 1 times the change in temperature is 2 degrees Celsius. So the correct answer is 18 calories. So the choice 18 is the correct choice. Used to measure the change in heat which take place by measuring the change in temperature which happen to water. The picture that we can see on the screen, that for what? The pump calorimeter. The pump calorimeter is used to measure the change in heat content by changing the temperature of water surrounding the calorimeter. Here we have a problem. When using a calorimeter, 0.28 gram of propanol fuel was burned. This raised the temperature of water by what? 21.5 degrees Celsius. The mass of water in the calorimeter equal 100 gram. Find the amount of energy resulted from burning this fuel. So we can say that Q, which equals MC delta T. We need to calculate the Q, the amount of heat produced from burning this amount of fuel. The mass of water that we have is 100 gram, and the specific heat of water, as we said, 4.18 joule per gram degree Celsius, times the change in temperature which took place is 21.5 degrees Celsius. So the quantity of heat that you are going to calculate will be in joules. You can do it on the calculator. Heat capacity. We talked about the specific heat, okay? But if we said that we have a piece of iron, okay, of 1 kilogram, and we have also a piece of iron, but 2 kilograms. We want to raise the temperature. Here iron, and also here iron. So we have what? The same specific heat for both of them. But we have different masses. So to raise the temperature of the first one by 1 degree Celsius, you need amount of heat less than the amount of heat required by the 2 kilograms to raise them 1 degree Celsius. So heat capacity is what? The quantity of heat required to raise the temperature by 1 degree Celsius. Here we have the same specific heat for the same substance, but because we have different masses, so we have different amount of heat. What are the factors affecting the heat capacity? As we said, the mass of the object and also the kind of substance. So if we have a substance with high specific heat, that means it needs high amount of energy. If we have another substance with low specific heat, means it has low amount of energy. The heat content or the heat enthalpy, the sum energies is stored in 1 mole of matter. As we know that there are different sources of energy, from the electrons, from the bonds between atoms, from the bonds between molecules. These all represent what? The heat content. The change in heat content is the difference between what? The total heat content of product and the heat content of reactant in chemical reaction, which is named by what? Delta H. Delta H says that H of product, the heat content of product, minus the heat content of reactant. The change is in standard heat content, or delta H standard, the heat content are calculated in standard conditions, which at 1 atmospheric pressure and temperature 25 degrees Celsius. Here we have a very important information, which says that the heat content of element equal 0 at standard conditions. The exothermic reaction. Exothermic reaction means the heat content of reactant is less than the heat content of reactant is greater than the heat content of product. So the difference in them come out as energy released with the product, as heat energy released with the product. So in exothermic reaction, you can find the amount of heat written with what? With the product, because it releases amount of heat. And in exothermic reaction, delta H has negative sign. Why it has negative sign? Because as we said, delta H is equal the heat of product minus heat of reactant. In this case, heat of reactant greater than heat of product. So the value of delta H will be negative. So in exothermic reaction, delta H has negative sign. What about endothermic reaction? In endothermic reaction, you will find the heat or the amount of energy is found where? With the reactant. Why it is found with the reactant? Because the heat content of product is greater than the heat content of reactant. So delta H has what? Positive value, because heat content of product is greater than heat content of reactants. So reactant need to absorb amount of energy to start. Here we have an example. 1 gram of hydrogen, 1 gram of hydrogen, where the molar mass of hydrogen equals 1, react as the following reaction. H2 plus Cl2 give us 2HCl plus 185. From the equation in front of us, we can conclude that the reaction is what? Exothermic reaction. Why the reaction is exothermic reaction? Because the heat is released with the product. So it is exothermic reaction. So delta H here should be negative. So the first one, or the first graph, represent endothermic reaction. And the second graph represent also endothermic, as the reactants absorb amount of heat. Here, C and D, so A and B, are excluded. For C and D, we can think about C and D. In C, the released amount of energy, negative 92.5. And in D, the released amount of energy, or delta H, equal negative 185. For delta H, negative, here delta H equal negative 185, but this for what? For the total mole, or 1 mole of hydrogen, which has mass of 2 grams. But here he is asking about the reaction of 1 gram of hydrogen. So we are going to divide this delta H by 2. So the correct answer will be C. The opposite energy chart. Which of the following reactions expresses the opposite energy chart? Here, this energy chart represents exothermic or endothermic reaction. We are going to look at what? The heat content of reactant and heat content of product. Product has greater heat content. So here, delta H will be positive. So the reaction is what? Endothermic. Endothermic reaction, as heat content of product is greater than the heat content of reactant. So let's check which one represent the graph. A plus B give us C plus 50. Here the heat is found with what? With the product. So it's exothermic reaction. So this one is not correct. A plus B plus 50 give us C. So heat is found with reactant. That means the equation, or this equation, represents endothermic reaction. For me, this one is the correct answer. Here delta H is negative, it's exothermic, so it's not correct. Here also C, A and B negative 50. That means it should move to the other side, the positive sign. So here it's also exothermic. So C and D also not correct. Bond energy and heat content. The bond energy, the energy required to break the bonds between molecules in 1 mole of matter. How to calculate delta H by using bond energies? The sum of energy absorbed in breaking bonds with positive sign, plus the sum of energy released from new bonds with negative sign. So we should write the chemical equation in a correct way and detect the number of moles, and also detect the way, the structure of the chemical formula that we have to detect the bonds of energy. In exothermic reaction, delta H is negative. So the energy, the sum of energy released from releasing bonds greater than what? The sum of energy absorbed in breaking bonds. Now, what about endothermic reaction? In endothermic reaction, delta H is positive. Why it is positive? Because the sum of energy absorbed in breaking bonds is greater than the sum of energy released from forming new bonds. Here we have an example. In the following reaction, H2 plus Br2 give us 2HBr. If the values of bond energies are shown in the following table, the change in heat content for the reaction is, we are going to choose from this choice. So, as we said, we have an equation. We should make sure that the equation is balanced. So here we have 2 hydrogen, and here 2 hydrogen, 2 bromine, 2 bromine. Okay, it's okay, it's balanced. What about the bond? The bond between hydrogen and hydrogen is a single bond. Here bromine and bromine, also single bond. Here we have 2 molecules of what? Of HBr. So we are going to calculate what? The energy absorbed to break bonds, which are what? 436, the bond energy between hydrogen and hydrogen for the reactant, plus 190, which equals 626 kilojoule per mole. This what? Energy absorbed to break the bond. The step 2, we are going to calculate what? Energy released by forming bonds. We have what? 2 molecules from HBr. The bond between them has energy of 362. So it will be 724 kilojoule per mole. Now we calculated the energy absorbed to break the bond, energy released to forming the bond. Now we are going to calculate delta H, which equals the sum of energy absorbed to break the bond, 626, plus what? Negative the sum of energy released by forming bond, which is 724. So it will be 89 with negative sign, 89 kilojoule, which is D. So choice D is the correct choice. Thermochemical equation. In thermochemical equation, it's not far from the ordinary equation that we are using. But in thermochemical equation, the equation should be balanced, okay? And also, we can use fractions to balance the thermochemical equation. In ordinary equation, we can't use the fraction, but here in thermochemical equation, we can use the fraction. Also, we should write the state, if it is solid, or if it is liquid, if it is gas. Why? Because the heat content for the same substance is different from one state to another. So for example, for water, it has heat content in liquid state different than the heat content in gaseous state, and so on. So we should write what? The state of matter in what? In the thermochemical equation. Also, the value and the sign of heat content. We should write if delta H is positive or delta H is negative to refer what? To refer if the reaction is exothermic or endothermic. Also, when multiplying the side of thermochemical equation, if we multiply one side of thermochemical equation, we should multiply the other side, and also we should multiply what? The change in heat or the enthalpy of heat. Okay, calculate the molar enthalpy of water from the following reaction. Here we have CH4 plus H2O give us CH3OH plus H2. Here delta H for this reaction, negative 78 kilojoule per mole. The molar enthalpy for CH4 and CH3OH, 75 kilojoule per mole, 229 kilojoule per mole respectively. Then calculate the absorbed heat when 64 grams of CH4 react with excess of water. So here we are going to calculate what the molar enthalpy of water. He said that delta H for this reaction equal delta H of product, minus delta H of reactant. Delta H here is negative 78 equals delta H of product, which are H2 plus CH3OH. CH3OH, its delta H is 75. No, 229. Plus, for hydrogen, because it's element, it will be 0. This is for product. Minus delta H of reactant, we have CH4, which is 75, plus delta H of water, which we want to calculate, delta H of H2O. So we are going to use the calculator. So here, negative 78, negative 229 equals negative 75, negative delta H of water. So negative delta H of water, H2O, equals, we'll move this to the other side, but first, negative 78 plus negative 229, negative 307 plus 75, which is equal plus 75. Welcome to part 2 of our revision. Here we are going to complete our revision. We will start Unit 2, Chapter 2. Unit 2, Chapter 2 is we're talking about the change in heat content accompanied with the physical change in the first lesson, and the second lesson is accompanied with chemical change. The change in heat content accompanied with physical change, like the heat of solution or the standard heat of solution, the amount of heat released when 1 mole of solute released or absorbed when 1 mole of solute is dissolved in a certain quantity of solvent to get a saturated solution in a standard condition. So in dissolving 1 mole of NH4NO3 in water, it gives us aqueous ions from NH4NO3. That means it dissolves in water. So here delta H has positive 25.7 kilojoule per mole. This equation represents what? Endothermic solution. So the solution which is formed is endothermic. Why? Because delta H has positive value. The second one, here NaOH plus H2O give us Na plus OH, NaOH which was solid, plus H2O give us Na positive plus OH negative. Here delta H is negative 51 kilojoule per mole. So in this equation represents the dissolving of sodium hydroxide in water in and forming exothermic solution. Why? Because delta H has negative value. To calculate the standard heat of solution, we use this rule, which says Q equal MC delta T. By calculating the Q, then we can calculate delta H of the solution, which equals negative Q over N, where N represents number of moles and Q represents the amount of heat. How explanation of standard heat of this solution. The dissolution process or dissolving process take place in 3 steps. The first step is separation between the molecules of solvent, in which delta H has positive value. It's endothermic process, so delta H value will be positive. For what? Separation between the molecules of solvent. Delta H1 will be positive. The second step, separation, but also between what? Solute particles. So separation between molecules of solute, endothermic process. Delta H2 will also has positive value. And the last step, dissolution process, which is exothermic process, delta H3. Or we can say that the third step is the combination between the solute particles, which are separated, and the solvent particles, which also are separated. This combination represents exothermic process. So delta H3 will have, or always have, negative value because it represents exothermic process. So the final delta H of the solution will be endothermic. The solution will be endothermic when delta H1 plus delta H2, which both of them have positive values, greater than what? Delta H3. So the solution will be endothermic. So delta H final for the solution will have positive value. Delta H1, if delta H1 plus delta H2 less than delta H3, so the solution will be exothermic because delta H final will have negative value. Or delta H3, which is representing exothermic process, the combination between solute particles and solvent particles, have negative value. The molar heat of the solution is the heat change resulted from dissolving of what? 1 mole of solute in solvent to form 1 liter of solution. So molar heat of solution is calculated from the relation delta H solution equal negative Q over N. The hydration means the attaching of dissociated ions with what? Water molecule. Here hydration represents the third step, which is delta H3. But here it is related only on dissolving what? Salts with water. So hydration is attaching of the dissociated ions with water molecules. Hydration energy, the amount of energy released from attaching of ions or molecules of solute with water. Finally, we have delta H dilution. So now we have a solution, okay? This solution may be endothermic solution, may be exothermic solution. We are going to dilute this solution. Also, a dilution can be endothermic dilution or exothermic dilution. The next one, the standard heat of combustion. As we know that combustion is a chemical change. So we explained the physical change such as forming a solution and the heat change which take place in physical change. And now we are going to calculate the heat change which take place with chemical changes or chemical process such as combustion. What is meant by combustion or heat of combustion? The quantity of heat, but usually what? Released on the complete combustion of 1 mole of substance in an excess amount of oxygen. So we can say delta H of combustion usually carry negative value. Why? Because it is representing a released amount of heat due to combustion. So how can we know the equation of combustion? We can know the equation of combustion from the reactant and the product. We will usually find the reactant. The reactants are represented by organic compound react with oxygen to get carbon dioxide and water with amount of heat. The equation of combustion, again, the combustion of organic substance usually take place in the presence of oxygen and produces carbon dioxide and water with releasing amount of heat. So delta H here will be negative. What about the standard heat of combustion? The amount of energy released from complete combustion of what? Of 1 mole of matter in standard condition. Another example, the first one is the combustion of propane, the second one, the combustion of glucose with oxygen to give the same products, which are carbon dioxide and water. Here, delta H is represented by negative value because the combustion is an exothermic process. Heat of formation. The quantity of heat released or absorbed during formation of what? Of 1 mole of compound from its constituent elements. The constituent elements, the origin elements, such as water, for example. Water is formed from what? Hydrogen and oxygen. So hydrogen and oxygen are the constituent elements. Also, the equation of heat formation could have only what? 1 mole of the product, and the product should be represented by only 1 mole. So it is heat of formation equation. The standard heat of formation, the quantity of heat absorbed or released when forming 1 mole from its element. Its element should be in a standard condition. Heat of formation of element equals 0. So if we are going to calculate delta H standard heat of formation by using heat of formation, so it equals heat of products minus heat of reactant, and here delta H will be the sum of heat of formation of products minus the sum of heat of formation of reactant. Here we have an example, heat of formation of methane, which is negative 74.6 kilojoule per mole. Carbon dioxide equals negative 393.5 kilojoule per mole. Water vapor negative 241.8 kilojoule per mole. Calculate the change in heat content of the following reaction. So we are going to calculate delta H for this reaction by using the heat of formation for each product. So delta H equal delta H of products minus delta H of reactants. Delta H formation for products minus delta H formation of reactants. So the product that we have is carbon dioxide. So what is the heat of formation of carbon dioxide gas? It equals negative 393.5 plus, in the product we have 2 moles of water. So it's 2 times the heat of formation of water, it's water vapor. So it equals negative 241.8. Okay, these are representing the delta H of the product minus delta H of reactant, which is methane negative 74.6 plus 2 moles of oxygen, and as we know that the heat of formation of oxygen equal 0. So we have only one heat of formation for reactant, which is the heat of formation of methane. So the result will be, we are going to use the calculator. So we have negative 393.5 plus 2 times negative 241.8. So equal negative 877.1. Here minus minus positive, so plus 74.6. So the result will be negative 802.5. So here delta H has a negative value, so it's kilojoule. Delta H here has negative value, so the reaction is exothermic reaction. Another example, if heat of combustion of 1 mole of C2H3OH is negative 1367 kilojoule per mole. So we have C2H3OH, okay, combusts in the presence of oxygen, for sure. So the product should be what? Carbon dioxide plus water vapor. And here we said delta H equals negative 1367. Now we are going to balance the equation. Here we have 2 carbons, so we are going to put here 2. Here we have 4 hydrogen, so we are going to put here 2. Now we have 4 carbon here and 4 oxygen here and 2 oxygen. Now it's 6. So we have remove 1, so we have 5, or we need 5 oxygen, so we are going to put 5/2 oxygen, so we have a balanced equation. As we said, that thermochemical equation, we can use fractions in thermochemical equation. Write a thermochemical equation which represents this reaction. In thermochemical equation, we should also write the states. So if we have ethanol, it's liquid, oxygen, gas, carbon dioxide, gas, water vapor, gaseous state. Calculate the energy released from combination of 100 grams of ethanol with oxygen. From the equation in front of you, we can say that 1 mole of ethanol, okay, 1 mole of ethanol, 1 mole of C2H3OH releases amount of energy. Here we have delta H is negative 1367. And as we said, delta H, if delta H is negative, the Q, or the quantity of heat, should be positive. So here the quantity of heat released from burning or combustion of 1 mole of C2H3, so it will be 1367. So by grams, I'm going to convert 1 mole of ethanol into molar mass. So it's 2 times 12, plus we have 4 hydrogen, plus 16. So 4 plus 16, it's 20, 20 plus 24, so it's 44. 20 plus 24, 44. So 44 grams of ethanol produces 1367 kilojoule. So if we use 100 grams of ethanol, so the amount of heat will be, the Q, or amount of heat, equals 100 times 1367 367 divided by 44. So it equals 3,106.8 kilojoule. Here, delta H, kilojoule per mole. Okay. Now we finished Unit 4, and we are going to start Unit 5, the nuclear chemistry. In the nuclear chemistry, we are going to deal with all what happened inside the nucleus. So we should express the element with a sample that explain for us what inside the nucleus. So we are going to use this formula to represent the different samples of elements with all details. So Z here, X represent the element, whatever the element. Z represent what? The atomic number. Atomic number means what? Number of protons. And A represent mass number. What is mass number? Number of protons plus number of neutrons. So if we want to calculate number of neutrons, will be A, which is mass number, minus Z, which is atomic number or number of protons. The isotopes are very important. It's a very important part in nuclear chemistry, isotopes, because they represent different images for the same element. This element has the same atomic number, the same number of proton, the same number of electron. So isotopes in chemical reaction are working in the same way in chemical reaction, but they are different in what? They are different in the mass number or the number of neutron, exactly. So they have the same number of proton, but they have different number of neutron. That's why they are different in mass number. So isotopes are the same elements, atoms of the same elements, which have the same number of proton, but different number of neutron. Hydrogen isotopes are proton, protium, deuterium, tritium. Proton or protium, from its name, it has only one proton inside the nucleus. Deuterium, do or deuterium, it has proton and neutron inside the nucleus. So the nucleus has two particles. Tritium, the nucleus has three particles. One of them is proton, and the other two are neutrons. The relation between mass and energy. Einstein said that any decrease in mass or any defect in mass is converted to energy, according to what? Einstein equation. The Einstein equation says that energy equal mass times constant square. In this equation, energy is represented by joule. Its unit is what? Joule. And mass is represented by kilogram. And c square representing what? The speed of light square, which is what? 3 times 10 to the power of 8 square. This is what? The first Einstein equation, because we have two Einstein equations. The first one, calculate the energy in the unit of joule by using mass in the unit of kilogram and constant, which is the speed of light square. The second Einstein equation, here it's calculating energy, but in another unit, which is what? Million electron volt. And mass here is measured by what? Atomic mass unit. Here the constant will be what? 931. But we have two equations for Einstein. The one equation which calculates the energy by joule unit, and the mass by kilogram, and the constant is the speed of light square. The second equation, represent Einstein equation, is calculating energy in million electron volt and mass by atomic mass unit, and its constant will be 931. Here we have some conversions that you should memorize them very, very, very well. The most important is converting between 1 atomic mass unit and kilogram. 1 atomic mass unit to kilogram, you should multiply by 1.66 times 10 to the power of negative 27 kilogram. So 1 atomic mass unit has 1.66 times 10 to the power of negative 27. 1 million, the other conversion, which is very important, from million electron volt to joule. 1 million electron volt equal 1.6 times 10 to the power of negative 13 of joule. These are the most two important conversion that you should memorize very well. Nuclear binding energy. How to calculate nuclear binding energy? Let's take an example, apply it, then you will know how to calculate the nuclear binding energy. Calculate the nuclear binding energy, he said what? Per nucleon. In calcium 2040, if calcium 2040 has mass of 40.0.78 atomic mass unit, and mass of proton and mass of neutron. So he gave us mass of proton, mass of neutron, and he gave us what? The actual mass of carbon. So we are going to calculate theoretical mass of calcium 2040 equals what? The mass of proton, number of proton that we have, 20, times their mass of proton, which is 1.007825. Okay, plus the number of neutron, 20, times their masses, which are 1.008665. Okay, so here the theoretical mass equal, I'm going to use my calculator. So it will be here 20 times 7825 plus 20 times 1.00865. So the result will be 40.3298. Okay, طبعا atomic mass unit. Here we should find that the theoretical mass is greater than the actual mass. This is a good hint that your calculation is correct. The actual mass that we have is what? 40.078. So the second step, I'm going to calculate what? Mass defect. Mass defect. The mass defect equals the theoretical mass, which is 40.3298, minus the actual mass, which is 40.078. So I'm going to use my calculator to get the result. Minus 40.078. So it equals 0.2518 atomic mass unit. So the first step, we are calculating theoretical mass. The second step, we are calculating the mass defect. The third step, we are going to calculate binding energy. The total binding energy. The total binding energy equals the mass defect that we calculated, which is 0.2518 times what? Times 931. We are calculating energy, so we are using the second Einstein equation. So it will be, so I'm going to use my calculator, times 931 equals 234.4 what? Million electron volts. Now I'm calculating what? The total binding energy. I calculated the total binding energy, but here in the question, he is asking for what? The nuclear binding energy per nucleon. How many nucleon do I have? I have 40 nucleon inside the nucleus. So I'm going to say that binding energy per nucleon equals total binding energy, 234.4, divided by what? Number of nucleons, which are 40. So I'm going to divide by 40 on my calculator. So the result will be 5.86 million electron volt. So each nucleon has energy or binding energy 5.86 million electron volt. So the nucleons are what? The number of particles which are found inside the total particles are found inside the nucleus, even if they are proton or neutron. The elements, we are going to classify the elements to light elements and heavy elements. Light elements, their atomic number not exceeding 38. Heavy elements, their atomic number is greater than 38. Atomic number greater than 38. So if the atomic number is less than 38, it's light element. Heavy element if the atomic number is greater than 38. So in light elements, we have stable light element, and we have unstable light element. In heavy also, we have stable heavy and unstable heavy. In light stable, the ratio between number of neutrons and the number of protons should be equal 1, or it may reach to 1.15, but not exceeding that. Unstable, the ratio of N over Z not equal 1, so it will not be stable element. For heavy elements, the stability of heavy elements, the ratio between N and Z may be reach to 1.53. It's accepted, so it's stable. Greater than that, it will be unstable. The ratio is greater than 1.53, so it will be unstable heavy element. The ratio between what? Number of neutron and the number of protons. Here, the nuclear stability. In the nuclear stability, we have 3 positions for instability. We have left position of the stability belt, we have right position of the stability belt, and we have the above position of the stability belt. The right position of the stability belt, in which number of proton compared with number of neutron is usually greater than number of neutron. So the ratio between number of neutron to number of proton is greater than 1. Okay? So it's unstable. Number of neutron is greater than number of protons. So in the left side, neutron will convert to proton. How neutron convert to proton? By emitting negative beta particle. Here plus negative what? Beta particle. يبقى neutron is converted to proton and emitting negative beta particle. On the right side, number of proton greater than number of neutron. So the proton will convert to neutron to reach the stability. The proton will convert to neutron and emits what? Beta particle, but carrying what? Positive charge. Above the stability belt, the nucleus is very crowded. So to reach the stability, it emits what? Alpha particle. What is alpha particle? Alpha particle is a particle consists of 2 proton and 2 neutron. So again, at the left side of the stability belt, number of neutron greater than number of proton. So to reach the stability, neutron is converted to proton by emitting beta particle carrying negative charge. At the right side of the stability belt, number of proton is greater than number of neutron. So proton convert to neutron and emitting beta positive particle. Above the stability belt, the nucleus is very crowded. So it is going to emit what? Alpha particle. What is alpha particle? Alpha particle representing 2 proton and 2 neutron. So 2 proton and 2 neutron are going outside the nucleus. What will happen when the neutron is converted to proton? What will happen to the atomic number? What will happen to the mass number? Because neutron is converted to proton, so atomic number will what? Increase by 1. But mass number doesn't change. Why mass number doesn't change? Because the neutron changed to proton. So if we remove 1 neutron, another proton is replaced. So mass number doesn't change. Here, the atomic number, the proton convert to neutron, so atomic number decreases by 1, but also mass number doesn't change. Okay, what if the element emits alpha particle? So the atomic number decreases by 2 and the mass number decreases by 4. Listen to the radioactivity and nuclear reactions. We have 3 types of radiations, which are alpha radiation, beta radiation or beta particle, and gamma rays. For alpha particle consists of 2 proton and 2 neutron. Beta particle represent negatively charged particle without any mass. Gamma radiation has no mass and has no charge. Half-life. Half-life is a property or the time in which the half number of the nuclei in radioactive element decay by means of radioactive decay. Here we have an example by which we can learn how to calculate the half-life. What is the original mass of a sample of element lead-210, which after passing 63 years, 0.125 gram of it remains, knowing that half-life is 21 years. So he told us about the half-life. The rule of calculating the half-life, we can say that number of periods, the periods of division, equals the total time divided by what? Divided by half-life. So we can calculate half-life by what? By dividing total time by number of periods of decay. So in this question, we want to calculate what the original mass after passing 63 years, knowing that the half-life is 21 years. So we are going to calculate number of periods. We have total time, which is 63, divided by the half-life, which is 21. So we have 3 periods. He said the remained mass after these 3 periods is 0.125. So 0.125 is the remain. So we are going to multiply it by 2. So it will be 0.25 gram, multiply by 2 one more time. So it will be 0.5, multiply by 2 for the 3rd period. So it will be 1 gram. So the original mass of lead is what? 1 gram. The nuclear reaction, we have nuclear transmutation, natural transmutation. This natural transmutation for unstable element, which make decay by itself to reach the stability. The first example, uranium, make alpha decay or produces alpha particle to get thorium, which is more stable. Carbon 614 makes what? Beta decay to produce nitrogen, which is more stable. Here we have a very important note that the atomic number of the reactant should be equal to the sum of atomic number of the product. So here the atomic number of reactant is 92, and the sum of atomic number of the products also 92. So here the equation is balanced, or the nuclear equation is balanced. Also, the mass number of the reactants should be equal to mass number of the products. By this way, you can find the question which is asking you what is the particle which is produced when uranium-92-238 is decayed to give thorium 90-234. So you are going to write the equation, try to balance it to guess the particle. If it is alpha, if it is beta. Here carbon give us nitrogen. So if we add 7 plus -1, it will give us 6, which is the atomic number of carbon. And also here 14 of carbon, the mass number of reactant, equal the sum of mass number of the products. This is natural transmutation. Artificial transmutation. In artificial transmutation, you are going to use a projectile or a bomb by using nuclear accelerator. Nuclear accelerator may be Van de Graaff accelerator or cyclotron accelerator. The projectile, we have different types of projectiles. We can use proton as a projectile, we can use deuteron, we can use neutron, and also we can use helium as a projectile. So, if we use helium as a projectile for nitrogen, this nitrogen was stable before using this projectile, but when using the projectile, we converted it into fluorine, which is unstable, and spontaneously decay to give what? Oxygen 817 and hydrogen 11. If we apply the conservation law of a charge, then we added the atomic numbers for the reactants. So here 7 plus 2, we have 9. And the atomic number of the product, so 8 plus 1 equals 9. And also, if we apply the conservation law of energy, of energy and mass, so if we add the sum of masses of the reactant, which are 18, they should give us the sum of masses of the product, which are also 18. Okay, let's solve together equation 1 and equation 2. We want to guess what will be the rest of the equation. So here, aluminum 13 plus 1 atomic number of hydrogen, so it's 14. So here in magnesium, it's 12. So we have X, which has atomic number 2. What about mass number? Here 27 plus 1, it's 28. Magnesium has only 24. So we need here 4 to balance the masses. So X, which has atomic number 2 and the mass number of 4, which is what? Alpha particle. Here in the second equation, 12 plus 1, 13. We have sodium 11. So we need here 2. In what? In the atomic number. In mass number, 26 plus 2, it's 28. And here sodium has 24, so we need also mass number 4, so it will be alpha particle, which is 2, 4. The nuclear fission, the last nuclear reaction in which the nucleus is split into 2 small nuclei. So uranium, when projectile with neutron, give us X and Y. This X may be barium or krypton, X and Y, with 2 or 3 neutron. So here we have an example, uranium 92, 235 plus neutron 01 give us krypton 36, 92 plus 3 of neutrons. And this is different from one equation to another. The nuclear fusion, 2 small, 2 light nuclei are fused together to give a heavier nuclei and producing neutron with a huge amount of energy. Each of the following is nuclear fusion, except we said in nuclear fusion, we are searching for what? Two light atoms fuse together to give a heavier atom. So here, is it H12 plus H13, H12 plus H12, H12 plus H12, or N714 plus N01? In this one, this is fission, not fusion, because we have a heavier atom, which is nitrogen atom. Usually fusion is related to hydrogen with all its isotopes. So nitrogen is projectile with neutron to give carbon 614 plus protein. So this is fission, not fusion. The rest are representing fusion. The nuclear reactors work with the fission reaction, which represent what? A series reaction. So uranium, if one uranium is bumped with a projectile, it produces different 2 or 3 neutrons. These neutrons complete to bump another uranium, which is broken into other nuclei and producing another neutron. As you can see, these gates are cadmium gates, which control this reaction. Control the reaction by absorbing these neutrons. As we can see in this picture, cadmium rods here, these are uranium rods, and these are cadmium rods. When cadmium rods are placed down, they slow down the reaction. When cadmium rods are raised up, they fast the reaction. Why? Because the role of cadmium rod here is to absorb the neutron which is produced from the splitting of uranium. Now we have an example. The sample X, Z, and A represent the nucleus of unstable elements, and to reach the stability, it loses 4 from what? Beta particle and 1 alpha particle. Okay. The sample of the nucleus, which is formed of will be what? So I'm going to write the equation by this way. Here I have X, Z, and A. Okay. Give us another X of unknown atomic number, unknown mass number, plus 2, sorry, he said 4 of beta particle. So 4 beta particle, which is E -1, 0, plus 1 of what? Helium, 1 of alpha particle, which is helium 2, 4. So X here has Z -4 plus 2. This is what? Z. And A plus 0 plus 4. So which one is the best choice? So it will be Z -2 and A -4, which is A. The second question, in the reactions, here nickel 2860 plus neutron give us cobalt and X. We don't know what is X. So from the equation, I'm going to look at the atomic numbers. Here 28, here 0, and here we have 27. So the atomic number here should be 1, okay? Mass number here 60 plus 1, it's 61. So the atomic number also should be 1. So the first x, or x in equation 1, represent what? Neutron or proton. As we know that neutron increase the mass number but not change, or doesn't change the atomic number. The one which change both of them is what? The proton. So A and B for me exclude. Another equation, or equation 2. Here, magnesium 12 plus helium 2, so 12 plus 2, 14. Here we have silicon 14, so the atomic number here will be 0. What about mass number? Mass number 24 plus 4, it's 28. And here 27, so we need only 1 here. So this X represent what? The neutron. Because neutron, the one which change the mass number, but doesn't change the atomic number. Now we finished all the revision. Thanks for all of you. Hope you all the success. Thanks for all of you. Assalamu alaikum wa rahmatullahi wa barakatuh.